going? Yes. Okay. So this week we're talking about functions. Does anyone know what a function is? I know last week I sort of gave you a trick question. What is a set? Yeah.
Something that maps from something to something.
That's a good way to put it. It's like a map, right? Yeah, it's something that maps from like some input set to some output set. We have different words for all these things because we're mathematicians, but you're computer scientists, so it's like an output to an input. It's literally a function in computer science. So again, we sort of run into the same issue we did with sets, right? Where it's like, you use the word map. Well, what's a map, right? And it's like you can keep sort of going back and having these issues. I'm going to give a definition that you might not be happy with, which is that a function is a set. Does anyone see how that works? What I mean by that, a function is a set. It's a kind of set. It's just a specific type of set. So for example, if we have, let's say we have a set here. We'll call this set A. And let's say it has three things. Let's say it has X, Y, and Z. Then I'll have another set. Let's say it has two things, maybe smiley face and sad face. So this will be set B. So if I have a function, I'm going to define a function f, which goes from set A to set B. This is our notation that we use. So it's a function that takes in something from A and spits out something from B. Okay. So let's say that maybe let's say that maybe X. You plug in X to the function, you get smiley face. You plug in Y, you get the sad face, and if you plug in Z, maybe you get the smiley face again. Got it? So this function is actually a set. It is the set X, smiley face, Y, sad face, and Z, smiley face. Right? These two things are the same. It's just like the interpretation of them that's different, right? So all functions are sets. They're just glorified sets. They might be infinitely long. They might have infinitely many things in them, right? Like if you had your function was like x squared, well, there's infinitely many points you could plug in, so the set's infinitely large, right? But functions are just sets. Now there's different kinds of functions. We have some terminology here. The first kind I want to talk about is one-to-one. And the second kind I want to talk about is onto. Does anyone know the like fancy words for one-to-one and onto? We have like some sort of math, sort of fancy words, yeah. Exactly. So injective and surjective. How do you remember this? I'll give you a trick that helps me. Surjective, if you speak like French or you're familiar with French at all, sur is like on, right? Say like sur is like on something. So onto is surjective, right? If you don't speak French, you could think like surface, like if you put something on a surface, right? Put something down onto a surface, so it's onto a surface, surjective, right? And it's kind of, that's just the way my mind remembers it, but whatever works for you to help you memorize the difference. Now, I'm going to tap my foot here. Just keep in mind that, well, how do I say this? You should know these. Specifically, you should know these terms by like 120, because we have a quiz today. And these terms might be on that quiz. Maybe, maybe not. Maybe I'm just throwing you off. I don't think I'm that mean. Yeah, so memorize those terms, the difference. If a question says, show that something is injective, know that you need to show it's one-to-one. Something says, show that it's surjective, know that means it's onto. Okay, so what's the difference? What do these actually mean? Well, one-to-one, or injective, we have two sets here. I'm not going to give them names, but just whatever these points are. Actually, let's say it's literally this exact map. So it looks like this, like that. This function is not one-to-one. It's not one-to-one, or it's not injective, because there's a point that has more than one arrow coming into it. In other words, you have two different outputs that give you this, or two different inputs that give you the same output. It's still fine, it's a function. It's just not one-to-one. Okay? So a function that is one-to-one maybe would look something like this. So I should write here, not one-to-one. This is one-to-one. So if I have a function that maybe looks like this, as an example, this function is one-to-one. It doesn't matter that we've missed something. For the one-to-one piece, that doesn't matter. All that matters is that each dot does not have more than one arrow. So you can't have two or more arrows coming in. So in other words, one-to-one sort of is like that the number of arrows coming into a dot has to be less than or equal to one. Right? So the number of arrows coming in can't be more than one. It has to be one or less. Right? Let's talk about onto. So with onto, onto means that you can't miss any possible outputs. So as an example here, this function is not onto. This is not onto, because you've missed a dot on the output, right? So if I asked you, like, well, what input would give me this dot? Well, there is no input, because that dot doesn't have a possible input that it connects to, right? An example of a function that is onto would be like, let's see here. Say a function like this. This function is onto. It's onto because every dot has at least one arrow. It doesn't matter for onto, it doesn't matter that there's multiple arrows coming into a single dot. That's only for one-to-one, right? For onto, all that matters is that every dot has at least one arrow. So, by writing using the same notation, every dot needs to have greater than or equal to one arrow coming in. Does that make sense? So if a function is on one-to-one and onto, we say that it is a bijection. And if we sort of like and these two criteria, that it has to have less than or equal to one arrows and greater than or equal to one arrows, then we get that, so if it has to have at most one arrow and at least one arrow, then it has to have exactly one. So each dot has exactly one arrow coming in. That means it's a bijection. Each output has exactly one input. Does that make sense? Cool. Now one last thing I want to cover is, what is a sequence? And this is another trick question, I'm sorry. Anyone want to take a stab at it? Yep.
Like a set of numbers with like a pattern to it?
Yeah, they don't actually have to have a pattern to them. But yeah, it's kind of like the difference between a set and a sequence, right, is that a set is not ordered, right? Whereas a sequence, you have like a first number, you have like a second number, right? The order matters in a sequence, whereas in a set, it doesn't matter. But another way you can think of a sequence, so usually we write sequences something like this. You know, it's like an, some set, or something like in round brackets, an. Maybe the sequence is like 1, -5, pi, e squared, I don't know, right? And it should keep going here. So it doesn't necessarily have to have a pattern to it. They usually do, right? In this case, it doesn't. But you can think of an, or any sequence, as a function. A function that maps the natural numbers, in this case to the real numbers. So if you give me an input of a natural number, say you give me the number 3, right? So the input, if you think of this as like a function, the input might be 3, the output is going to be pi, right? Because pi is the third thing. Now we never actually write it like a function, we write a subscript 3 equals pi, right? But a sequence is a function. It's just a function where the input, the domain, are natural numbers. Does that make sense? Cool. Okay, I'm gonna stop the recording here.